Yeah, okay. So we are looking into this particular topic of role of antenna in communications. So I'll be discussing about the basic things related to antenna and hope it will be useful for you for your preparation for your placements also. So this is coming to this antenna's definition. So basically we know that antenna is a metallic apparatus for sending or receiving the electromagnetic waves. So it is usually a metallic device for radiating or receiving the radio waves, or you can also call it as a transitional structure between your free space and the guiding structure. So basically we know that whatever we are talking about communications, it's basically with respect to some channel or something. Whereas here we are talking about wireless communication, where you are talking about propagation of wave into free space. So this is what is basically the functionality of an antenna. So it is basically aiding or helping in the basic smooth transition from a transmission line into free space. So whenever you do that, there is basically a lot of impedance changes which you observe exactly at the end point of your transmission line. So a general, when we say transmission line, we say it's a characteristic impedance is 50 ohms. Whereas when you talk about free space, it's basically 377 ohms, the free space impedance. So there is a change, impedance change, which is happening with respect to your transmission line and free space. Now antenna basically serves as an impedance matching device. Okay. You can also call it as a transitional structure, or you can call it as a apparatus which is used for sending or receiving the waves. So whatever you call it, so basically it is that kind of thing which is helping for the propagation of wave into free space. So when you talk about antennas, we talk about several other concepts apart from the basic functionality of antenna. Like we also need to know what is radiation. We also need to know how this radiation happens and all these things. Okay. Coming to the equivalent circuit of an antenna, if you talk about the equivalent circuit of an antenna, so here you can see I have given that equivalent circuit of an antenna also. So if you consider that antenna is part of your transmission line, you generally consider it to be a load to your transmission line. So antenna can be considered as a load. So when you say a load is basically a kind of a device which completely absorbs or which doesn't reflect back. So when does the reflection doesn't go back? So whenever you have a proper impedance matching at the end point. So if you are terminating your transmission line with an antenna, basically you are aiming for your source signal, whatever has been generated, to reach your antenna and to be absorbed by the antenna. Now here in our case, antenna is basically projected as if it's a terminating impedance. Okay, whereas it's basically the functionality, whatever it is doing is basically it is absorbing. It's not absorption, but it is basically aiding for the smooth transition of your wave from the transmission line into the free space. So if you are considering an antenna can be considered to be a resistance. You can represent it as a terminating impedance, or you can represent it as a resistance which is having an equivalent resistance of say RR, which is called as radiation resistance. So this XA is basically related to the imaginary part of your impedance, whatever you take into account, which can account for the losses, or anything. So RL is basically the loss resistance, and whereas your RR is basically the radiation resistance. Okay, so XA can be considered to be the imaginary part, which is considered to be the loss. So RR is basically the main resistance, which is basically indicating how much amount of power is being taken up by the antenna. So this transmission line is having some the waves, whatever have been generated by your source, they are basically being transmitted by the transmission line, and at the end point you have an antenna which is taking up this wave and it is allowing it to transmit into the free space. Okay, so this is what is called the antenna equivalent circuit. Okay. So similarly, when you talk about in the context of mobile phones and all, so majority of the 5G smartphone designs, they were found to be using this Qualcomm modem and RFFE. RFFE stands for radio frequency front end section components. So this is basically indication that there is a lot of technical leadership of Qualcomm, especially in the microwave technology or microwave 5G technology, especially millimeter wave 5G technology. So having a complete modem to antenna solution is very critical here when you're trying to establish these 5G connections and especially these 5G networks. So this is a main critical thing because basically this kind of a setup will help us in optimizing the signal reception as well as for low power consumption. So signal reception is very important for us when we talk about the mobile things, right? So that is very important, and similarly consumption of power. So that is also a critical thing. So here basically when you talk in the context of antennas, the signal reception is what we are looking at, or that is the main thing which we are aiming for. Okay. So here what you need to know in this context is basically you should understand what is the basic antenna function. You should also understand what are the basics of radiation mechanism, how the radiation happens, and then because you know that we are talking at RF frequencies, that is high frequencies, so we generally go for microstrip antennas. So I'll not be discussing much about the other antennas because in this context, basically microstrip antennas are more critical here or more important for us. So this is what is a microstrip antenna or a patch antenna, which it looks like. So I think definitely the structure and all is known to you. So it's basically consisting of a ground plane followed by a substrate, and then you have a patch which can be in the form of a circle or a square or a rectangle. You can take any geometrical regular shape which you can aim for to be having the what do you call the shape of the patch. Okay, so this patch also will have some width and also will have some thickness. It is also going to have some length. So length, width and thickness are basically going to determine what will be your radiation pattern emerging out of this patch antenna. So this is the context which I am trying to start off with. So next, what are the main important things which we have to know in the context of this antennas? So main things are you should first basically know the classification in antennas. So what is the basic classification in antennas? Apart from the types of antennas, I'm talking about the classification of antennas. So classification means basically we have three different kinds of antennas. One which we call it as isotropic antennas, directional antennas and omnidirectional antennas. So here I have clearly given out some figures related to the applications of isotropic, directional and omnidirectional antennas. So here in a isotropic antenna, what do you mean by isotropic antenna? So the isotropic antenna is basically what do you call a antenna which is radiating equally in all directions. So here I have given you an example of a sun. So sun basically emits radiation equally in all directions. So this is what is an example for an isotropic antenna. So when you consider directional antennas, so directional antennas are basically giving out the radiation in a particular direction. So when you are aiming for radiation in a particular direction, you can take the example of a torch. So a torch is basically used to aim in a particular direction. So just like that, your directional antennas also, when you're talking in terms of directional antennas, the radiation, whatever we are trying to project, is basically in an intended direction or in a required direction. Then comes your omnidirectional antennas. So omnidirectional antennas are basically which emit radiation in a particular plane. So they are confined to a particular plane. So for example, if you take the case of a candle. So the candle is basically if you put a candle on a table in a dark room. So what generally happens, you see that the entire room is lit. Okay, the entire room is brightened because of the presence of the candle. But whereas the source where you have put it, that is on the table. So now below the table, you generally don't have any kind of light. Okay, so that is why it's dark, completely dark. So which means that it's scattering only a particular plane. So that is why it's called as omnidirectional. So omnidirectional antennas are the ones which give radiation confined to a particular plane. They don't give it in the entire thing. And isotropic antennas, though we say that it is radiating equally in all directions, they're not the practical antennas which we use. They are just the antennas which we say take it for reference sake. So whenever you are trying to project, or whenever you're trying to take a comparison between your directional or omnidirectional, now your isotropic antenna will serve as a reference for that case. So that's the reason why we go with directional or omnidirectional antennas. Okay, so this is the basic classification of your basic classification of your antennas. So isotropic, directional and omnidirectional. And as I said, isotropic is just a theoretical concept which was established for the referencing. So what we are basically looking when we talk about practical antennas are directional and omnidirectional. So which one we are taking into consideration? So similarly, when you talk about the planes of radiation, so there are two planes which we generally discuss whenever we talk about antenna radiation. So one which we call it as elevation plane, the other one which we call it as the azimuth plane. Now elevation plane is something which is basically starting from your z-axis with reference to your z-axis, at how much amount of angle it is there. So that is basically measured as your elevation angle. Okay, whereas when you take the azimuth angle, you are basically considering with respect to the horizontal plane, or which we also take it as x-axis is the reference to start your azimuth plane. Okay, so basically if you remember your spherical coordinate system, we are talking about theta and phi. So two things. So here there is a figure which is projecting basic things like your radiation pattern. Okay, so this is basically a figure indicating your radiation pattern. So here this is your z-axis, which is called as your main lobe axis. So this blue colored one is basically your main lobe. The main lobe indicates that the majority of your power is basically in what you call confined to that particular area. So whenever you talk about antennas, we talk about in terms of the radiation pattern. So when you talk about in the radiation pattern, we are looking at main lobe and also what are the side lobes. Side lobes are basically ones which are getting distributed in other directions other than the intended direction. So here your intended direction is in the z direction. So that's why the major lobe is in the z direction. Whereas there are certain lobes which are coming in different directions apart from the z direction. So these lobes, whatever are getting distributed in the other directions, they are called as side lobes. So in these side lobes also you have back lobes. Back lobes are basically those lobes which are exactly opposite to that of your main lobe. So 180 degrees phase shift. You do have a 180 degrees phase difference between your back lobe and your main lobe. So exactly opposite to your main lobe, you get your back lobe. So whether it is a back lobe or a side lobe, these are basically the lobes which are not required for us, or you say generally it's a wastage of power. Because whenever you are using an antenna, you are basically aiming in a particular direction. Mostly we talk about directional antennas or omnidirectional antennas. So in any of these cases, we are aiming for putting all our power or all our source signal into a particular lobe, which we call it as the main lobe. So the field or the major lobe or the main lobe, whatever you call it, so that is basically should be carrying your most of your energy, entire energy. So if anything is going into other directions, it's basically a wastage of energy which are going into side lobes or whichever is going into your back lobe. Okay. And similarly, when you consider about your radiation pattern, since we are talking in free space, so it's really what you call easy for us to analyze anything in the spherical coordinate system. So that's the reason if you see most of the things whatever are mentioned in your antennas radiation especially, so we talk in terms of R, ER, E theta and E phi, because they are the spherical coordinates which we have. R, theta and phi are the spherical coordinates which we have and generally we talk in terms of these things only. Okay. And similarly, when you talk about, as I told you, I was talking about elevation plane and azimuth plane. So elevation plane is this one which is from starting from your z-axis, at what point we are talking about. So that is indication of your elevation plane. So theta is basically an indication of your elevation plane. So theta will be equal to 0 at z-axis, or here in this case it is the z-axis. Okay, so from here whatever you are taking the angle, so that becomes your elevation plane. Similarly, when you talk about azimuth plane, we are talking about with reference to the horizontal plane, which is your xy plane, or which you say that the origination of your phi is basically at the x-axis. So phi will be 0 at x-axis, and whatever you are moving in the anti-clockwise direction from the x, so that will be taken as your azimuth plane, or the azimuth angle, whatever you say. Okay, so these are the two planes which you need to know. So because why you need to know this is because whenever you talk about radiation, they generally mention in terms of elevation plane and azimuth plane. So in that case, you should be aware of what they are generally talking about. Okay, and similarly, when you take the case of field zones, so you also need to understand what are the antenna field zones. This is again another important thing which you need to know when you talk about antennas. So antennas basically have three zones or three zones which we call it. First one, which is surrounding your antenna, is basically called as your reactive near field region. The one which is the next one is called as your radiating near field region, and the last one is basically called as your far field or your Fraunhofer region. So what is reactive near field region? Reactive near field region means that region which is immediately surrounding your antenna. So that is called as your reactive near field region. So the reactive near field region is the region where the force on the antenna will be more on the radiation or will be more on the waves. Okay. So in the previous slide, we have shown you how the radiation mechanism happens. So here there are lines of force which are extending starting from your source, and once it reaches the transitional structure or your antenna, it's basically getting detached from the line and it is moving out into the free space on its own. Okay, so this detachment, whatever is happening at this point, so that is what is basically termed as radiation. So once it is able to detach from there and go into the free space, then it is termed to be the radiation has started. Now, just as it leaves the transitional structure, it can't be termed as radiation. So that is what we are looking at the field zones. In the field zones, we'll get to know where exactly do we say it's radiation. Okay. So in the reactive near field region, basically, so there is the wave is trying to get detached from the antenna, but still the antenna has a good hold on the waves. So that means it will not allow it to detach. So the waves will be extending from the by having a support at the transitional structure or at the edges of this dipole, whatever is shown here, but it will not be able to leave it and go out immediately. Okay, so that is where you call it as a reactive near field region. It is indicated by R1, which is given by 0.62 root of d cube by lambda, where d is nothing but the aperture of the antenna and lambda is nothing but the wavelength concerned to the frequency wherever you are operating. So here, this reactive near field region is basically where you can say that the waves are not completely getting detached from the antenna. The waves are still having a control from the antenna perspective. And then when you enter the radiating near field region or your Fresnel region, which you call it, so this is where basically the force by your antenna will be dependent on the distance from the wave. Okay, so that means the wave has gone up to a certain distance. Now depending on where your wave is, the amount of force exerted by the antenna on these waves, whatever have got detached, will be dependent. So for example, if I say here you have something, okay, just after R1, here you have a point, and exactly at the threshold of R2 you have another point, 2 points if you consider. So here the amount of force will be more compared to this point where you are almost reaching to the end of your R2. Okay, so that means basically it is dependent on the distance. The closer you are to the reactive near field region, the more the force. The closer you are to the basic last region, that is your far field or your Fraunhofer region, the amount of force will be less. So that is what is your radiating near field region. But once it crosses this R2, which is defined as 2d square by lambda. So once you cross this distance, that is where you call it has entered the far field or the Fraunhofer region. Now this is more critical for us because once the waves are getting out into the far field or Fraunhofer region, so that is when you basically term it as radiation. You call it as radiation only when they enter the far field region. So that means they have to cross this distance of 2d square by lambda in order to enter this far field or the Fraunhofer region. And once it has entered, you can say that it has completely detached or radiation has happened. Okay, so that means you can try to use a receiver at any of this point after the radiating near field region or in your far field region. Basically, you should have your receiver placed only in the far field region, not any other region. So if you are putting in the reactive near field region or radiating near field region, it's of no use because we don't term it as radiation itself. We term it as radiation only when it is able to cross this barrier, that is, it is able to cross this distance of 2d square by lambda and enter into the far field or your Fraunhofer region. So once it enters in this domain into this far field or Fraunhofer region, that is when you call it as a radiation. So you have to always place your receiver in the far field region or your Fraunhofer region. Or in the other way of saying it, there is a minimum distance criteria which has to be maintained between your transmitter and receiver, which is defined by this R2. So you should always maintain a distance which is greater than 2d square by lambda between your transmitter and your receiver. Okay, and similarly, if you look at this particular thing, so this is basically an article which was given where the selection of major RFFE components. So radio frequency, what do you call radio frequency field effect parts, whatever front end section, whatever parts are there. So from the Samsung Galaxy S10 plus 5G. So these are the products, these are the things which are mentioned as part of the Samsung Galaxy S10 plus 5G, where you can see that most of the parts are procured from Qualcomm. So Qualcomm is very proactive in this particular region of antennas, RF antennas, millimeter wave antennas. Also, it has given a lot of modules related to these things, which are used in all the major prominent mobile providers. Apart from Samsung, even OnePlus uses Qualcomm, even your LG uses Qualcomm. So there are a lot of mobile companies, all the major companies use only the Qualcomm products in their 5G networks, or I mean in the 5G whatever they are going to bring it out, because these are the things which are having an edge compared with the other technologies or other companies also. Okay, so RF front end section is the major critical part to establish this technology in a proper way into your mobile phones. So that is being given very easily by your what you call Qualcomm. So that part has to be taken into account. And coming to the next thing that is related to the antenna. So this is what I've told you, the azimuth plane and the elevation plane. So here the same thing which I have indicated in the terms of the E field and H field also. So when you talk in terms of E field, we are talking in terms of the elevation plane. When you're talking in terms of H field, you're talking in terms of the azimuth plane. Or here it's basically, you know, that electric and magnetic fields are mutually perpendicular to each other. So there is a phase difference of 90 degrees between your E field and your H field. Okay. So this is what is related to your zones, field zones and planes of radiation. Okay. And also the basic classification. So next, coming to your antenna radiation pattern, as I told you, it's basically a graphical representation of the spatial distribution of radiation as a function of angle. So here there is an indication of all the lobes here. So first one is main lobe. So these are your side lobes or minor lobes, whatever you call it. This is your back lobe. So I think this picture gives you more clearly how a back lobe is placed. It is exactly opposite to that of your main lobe. And similarly, you also have another important term which we call it as HPBW, which we call it as half power beam width. Okay, so half power beam width is basically we are trying to take that particular distance or that particular variation in angle which is mentioned here. Okay, so that angle is measured as half power beam width, which is exactly half or 50% of your power. So if I take the main lobe here, so the edge is basically 100%. Whereas if you take these 2 points, these are basically 50%. So you are taking your half power. HP is half power beam width. So beam is nothing but your major lobe. So in this beam, wherever you are having half power, those are the 2 points which you will take into consideration, and the angular difference between these 2 points is basically taken as half power beam width. So whenever they mention any specifications related to antennas, this is the first thing that they give in order to design any antenna. So what is the half power beam width? So that means these are the points. If you are maintaining a half power beam width of this much, so exactly based on that your major lobe is going to be there. So any design, antenna design comprises of these important parameters. That is, one is half power beam width and the other one is beam width between first nulls. Okay, which we call it as beam width between first nulls or FNBW also. You call it the other way also. So what is beam width between first nulls? So basically you have a major lobe and you also have the minor lobes or the side lobes which are distributed on either sides. Now before the major lobe what you call completes or before the major lobe terminates and the side lobes start, there are certain portions where you get a zero also. Zero in the sense you don't have any radiation in that particular point. So immediately after the major lobe, wherever you are getting the first null, null means zero. So wherever you are getting the first null, so that point is taken as your first null points. So these are the two first null points which are taken into consideration, and the angular width whatever is there between these two first null points, that is being termed as beam width between first nulls or FNBW. Even this is given as one of the important specifications in your antenna design, where they try to see that how you are establishing your major lobe. So if your design is taking into consideration this FNBW and HPBW, it will be able to give out the radiation pattern in the required intended direction based on your design. Okay, so that is how you design this antenna. Similarly, when you talk about patch antennas, okay, so here you have an array of patches where you see that there are a lot of patches. Instead of a single patch, you can have multiple patches also placed on the substrate, so which acts like a array antenna. So this is basically a patch array antenna which is used. So why it becomes important for us to know about this patch antennas and all, or the array antennas, is if you look at the mobile towers or the mobile antennas, so basically they will be serving the, what do you call, the signal, or they'll be radiating the signal in different directions. So this is basically case A is basically 3 arrays serving in 3 sectors. So this is a sector which we call it. So the sector basically includes both the, the sector basically includes both the major lobe as well as your side lobes. So here it is given that the sector is 120 degrees. So 120 degrees means there is a coverage of 120 degrees from your antenna in this direction. So like that you can have different sectors. Okay, so there can be overlap of sectors also. Okay, so this is a sector antenna. Similarly, if you want to have a desired steering in a particular direction, like suppose I want to have radiation specifically in this direction. Okay, so in that case also you can have an antenna which you can project, or you can have a series of antennas or an array of antennas which can give you radiation in that particular direction. So that is what is called desired steering direction. So definitely you will also have undesired lobes and all these things, but you are basically aiming for radiation in a particular direction. Okay, so in that case also you can steer your antenna beam. Just like you steer your car, you can steer your direction of the antenna beam also if you have these kind of arrays. Okay, so basically how they steer the antenna is they create some kind of a phase difference. Okay, so phase difference between the array elements which can help in steering the antenna in a particular direction. So array antennas basically have the functionality of improving the gain. Okay, so when you are having a single antenna, you generally are catering only to a particular point. Okay, whereas you are catering to a particular directivity or a particular gain. Whereas when you talk about patch antenna, or whenever you talk about array antennas, it's nothing but the combination of several series of elements. That means you're bringing in a lot of elements which can basically increase your gain, okay, or increase your directivity in a particular direction. So that is how you are using desired steering. Desired steering means you are basically trying to avoid these undesired lobes or the side lobes or the back lobes, and you are trying to put entire thing into particular direction, which improves your gain, overall gain also, and your directivity also. So, and similarly, these are the examples which you can see for the omnidirectional, directional, and sector coverage antennas. So this is what is your omnidirectional antenna, so which is catering to a particular plane. Whereas if you represent in a two-dimensional way, it's simply a circle. Similarly, this is your directional antenna where you are directing your antenna beam in a particular direction. So which can be represented like a lobe or a beam. Okay, and similarly sector coverage, as I was discussing here. So you have a sector coverage where your antenna is covering a few sectors. So that is from here this angle to this angle, this angle to this angle. So all this can be done using your array antennas. When you are going for array antennas, these are the things which will help you out in establishing the radiation in a particular direction based on your requirement. And similarly, when you talk about the important parameter which we talk here is gain actually, or directivity. Okay, so instead of saying gain also, mostly we talk in the context of antennas with respect to directivity. So directivity, how do you get this directivity? So directivity is basically the ratio of your maximum power to your average power. It's basically a dimensionless ratio because both are powers only, and it will definitely have a value which is greater than 1, because since you are having the maximum to average. Okay, so you can also find this average by using 1 by 4 pi double integral p of theta comma phi d ohm. So where d ohm is nothing but the beam area. Okay, or you can also find it by knowing this formula 4 pi by ohm A, where ohm A is nothing but your beam area. So these are different formulas. I am not discussing further on this. Just wanted to show what are the main things which you have to remember. And similarly, when you say normalized power, you have to remember that you are dividing your power with the maximum power. That is when you call it as a normalized power. So sometimes when you talk in terms of radiation pattern also, here sometimes what happens is instead of saying major lobe, they might give you a normalized power pattern also. So in that case also you should be able to analyze. So it's nothing but where you are dividing with your power with the maximum value. That becomes your normalized power. Okay, and these are the various ways in which you can find your directivity. So you can divide by maximum power to average power. You can do 4 pi by ohm A, where ohm A is nothing but your solid beam area, and here D is nothing but 4 pi AE by lambda square, where AE is nothing but your effective aperture of your antenna. So using your aperture also you can find out your directivity. So these are the things. And similarly, as I told you, we are keenly looking into spherical coordinate system in order to obtain the values related to this antenna or the antenna radiation parameters. So here when you talk about the area, differential area, whatever you are considering in a spherical coordinate system, you already know that this is r square sine theta d theta d phi, which is in spherical coordinate system. So main important thing which you have to remember in the context of antennas and the radiation is that here we measure in terms of solid angle instead of the regular theta or phi, whatever we know in spherical coordinate system. So we define by an angle which is called as a solid angle. Now this solid angle is basically given with sine theta d theta d phi, or you also measure the solid angle in steradians. So steradian is also basically is nothing but where you are considering an equivalent area, whatever you take on the case of a sphere. So that equivalent area is nothing but you take the case of a sphere. So whatever this area r square is subtending at the center of your sphere, so that angle is basically called as your steradian. Okay, so you generally measure antenna solid angle in terms of steradians. So that's the reason this unit has to be familiar with you or related to antennas. Then coming to your different kinds of antennas which we have. So basically we have the first and the foremost which we discuss generally in context of antennas are your wire antennas, which are the simple antennas. So we have half wave dipole and monopole also. So half wave dipole is the antenna which is having a length of lambda by 2, and whereas monopole is one which is having a length of lambda by 4, exactly half of that of your dipole. And similarly, when you look at monopole, it is basically having a ground as the ground is one side, and the other half is above the ground. So that means your one of the source terminals is connected to the ground. So this is what is a monopole antenna. Whereas the same thing, if you have on both sides, that is if you are having a length of lambda by 4 and lambda by 4, with your source connected in between at the center, so that is why that is what is called as a dipole antenna. Okay, so here you have the charge distribution where you have the charge concentration at two ends of the pole. So that's why it's the reason why it's called as dipole, two poles. So you have a charge concentration at the ends of the dipole. So this is basically the current distribution, how it will be in the case of a dipole. Mostly it will have a sinusoidal current distribution where you have maximum current at the center and towards the edges it will be 0. So that means where you have current maximum, you will have voltage 0. So at the center point, voltage is 0. Okay, and this antenna which you see on the top of your cars and all, so that is basically a monopole antenna. Okay, so which is also called as a whip antenna, monopole antenna. So you generally use your antennas on the car for your radio signals and all, FM and all, you use this. So this is what is a car antenna. Similarly, when you come to the radiation pattern of a dipole, it is basically a figure of 8. Okay, so here you can see it's a figure of 8. When you, it's a basically a downward shape of kind of thing which you get as a radiation pattern for dipole. So if you cut it exactly at the half, you get what is the two-dimensional pattern for this, and here it happens to be a figure of 8. So the figure of 8 is basically the radiation pattern which we are seeing here, and that is the radiation pattern which we generally use to say about dipole. So when you say what is the radiation pattern for dipole, we generally draw a figure of 8. Okay, so which will be bidirectional, where your dipole is placed at the, this is dipole axis, and your lobes are basically spread out on either direction. So here if you see, it's completely, it's covering the entire what you call through in all ways it is covering the what you call the radiation is covering in the case of a dipole. Now similarly you also need to know that since we have discussed about monopole and dipole, so monopole is having a length of lambda by 4, dipole is having a length of lambda by 2. Now suppose you have a wire antenna which is having a length greater than this. So what happens? So definitely you will see a change in the radiation pattern. So here you can see this is a radiation pattern which you get for a length of lambda. If you look at the other one, this is for 2 lambda, this is for 3 lambda by 2. So see, you can see how the radiation pattern is changing. See, when you have a length of lambda or when you have a length of lambda by 2, so it's basically a figure of 8. Whereas when you are increasing the length further, so now your major lobe is basically establishing into 4 lobes again, and similarly here if you take it is establishing itself into 6 lobes apart from the side lobes. These are all the major lobes only. So apart from the side lobes, they are establishing themselves into different directions. So basically, when you're changing the shape of your antenna, or whenever you're changing or bringing in a change in the dimensions of your antenna, so everything is going to change or project a change into your radiation pattern. So that means you can clearly observe the change whatever you do in your length or whatever you do. So that is being reflected in your radiation pattern. So similarly, in the context of wire antennas, we can also talk about loop antennas. So loop antennas are basically a wire which is wound in the shape of a loop. So you can have a circular loop, you can have a square loop or a triangle loop or a rhombus, so anything. So even your folded dipole also comes under the category of a loop antenna only because it's a closed structure again. Okay, examples of these loop antennas are the antennas which you see on your music systems basically. So the one which you see here, this is on the top of, generally was used as an attachment for music systems where it was used for better reception of signals. So here it is written also AM loop antenna. So it's basically for use for reception of signals, radio signals. And similarly RFID also uses loop antenna. So basically loop antennas are used mostly as receiving antennas rather than transmitting antennas because they are very good receivers. Okay, so even when you take the case of a patch also, when you are designing your patch antennas also, so generally what they do is if you are using only exclusively for the purpose of receiver, so then they try to take the shape of a loop because that helps a lot. When you are taking the case of a loop, it is a better receptor rather than a transmitter. Okay, so that's the reason why the loops are preferred mostly as receivers. So whenever you want to just tap in the information or just receive the information, so that is when your loop antennas can be of major help because they are exclusively used for reception purpose. Okay, and coming to the receiving pattern of a loop, it also looks exactly the same as your dipole antenna, just like having two lobes, just like your dipole pattern. And you know the projections of your electric and magnetic fields already. So these are the electric and magnetic fields which are projected. So both are which are mutually perpendicular to each other. Okay, so that is the case of your loop antennas. Next, coming to another important thing which we have to discuss in the context of antennas are array antennas. So as I was telling you, array antennas carry a major role, especially right now in the practical situations. Lot of array antennas are being used basically in order to get a very good directivity or a very good gain. So here you can see the photo of a satellite communication or a satellite where a major large array was used basically to improve the gain or to improve the radiation pattern. So this is what is a array of elements which are being used here in satellite communications also, and there are a lot of antennas, not just these array antennas. You have lot of antennas serving for various purposes. Okay, so some are for steering purpose, some are for Bluetooth, some are for other things. Okay, so there are a lot of antennas which come in the context of satellite communication. So anywhere, wherever you are using antennas, the main major concern is the miniaturization. So when you are operating at low frequencies, definitely you can't decrease your size of antennas. Whereas when you are operating at high frequencies, especially in the microwave frequencies, you always have this feasibility of reducing the size. The size is a major constraint anywhere, and especially in the context of antennas also. So your patch antennas come as a major help to most of the things. So in your mobile phones also, if you see, so it's a very miniaturized thing, and nowadays you are getting more and more sleek mobile phones. Now how is it possible? Because you're getting everything miniaturized, and in that also you also have your antennas also which are getting miniaturized. Now how are the antennas getting miniaturized? Again, same thing, you are using either a microstrip or an array of microstrip basically to bring down that. Whereas if you see these huge antennas, either your parabolic antennas or your helical antennas or your turnstile antennas, so these are huge structures. Why are they huge structures? Because they are operating at low frequencies. See, always the antenna size is dependent on the wavelength. Now when you are operating at low frequencies, definitely your antenna size will be in the order of the wavelength, and since you have low frequency, the wavelength will be more. So since wavelength is more, antenna size is more. Okay, so based on that you generally have this. So that's why you see a lot of applications coming up in the microwave frequencies, which are high frequencies, because miniaturization is possible only at those frequencies. Okay, and here if you come in the context of array antennas, you need to know again there are two classifications in the array antennas also. One which we call it as broadside array, and the other one which we call it as an end fire array. So what is broadside array and what is end fire array? So here, depending on the spacing which you provide between the elements, okay, and the phase difference what you provide between the individual elements, So there is a variation in which you can establish your radiation pattern. So the one where you are getting a radiation pattern exactly perpendicular to their array elements, that is what you call it as a broadside array. Okay, so that means here the radiation pattern is exactly coming perpendicular to the line joining the elements. So here these are the elements 1, 2, 3, 4, 5. The antennas are shown. These are the elements which are being kept over here in a line. Okay, so if the radiation pattern is establishing itself in a direction which is perpendicular to the line joining these elements, that is when you call it as a broadside array. Whereas when you take the case of an end-fire array, so these are the elements which you have, and these elements are basically also placed in a line, except that they do have a phase difference, okay, between them. That phase difference which is equal to pi. So when you have a phase difference between the individual elements and you have placing them in a single line, so then you tend to get a radiation pattern which will be exactly along the line joining the elements. That is where you call it as an end-fire array, where the radiation pattern is establishing itself in the same direction as that of your elements. That is where you call it as a end-fire array. So this is the case of an end-fire array where you see the radiation pattern along the length of your array. Okay. So this is about your array antennas in general. There are a lot of types of array antennas, but these are the major things which you have to know about array antennas. And coming to the advantages of array antennas, as I was telling you, the major advantage is the gain and the directivity, what you can afford to have. And similarly in an array also, we have one more advantage, that is even if one of the element goes bad, in spite of that the antenna is functional. Okay, you are not completely losing out on the signal. The antenna is still there. There are other elements which will be catering to the radiation requirement, but may not be in the same precise way, but it is still operational. So that's the major reason why even if you go for array antennas, even if one element goes bad, the other ones will cope up with the loss and they'll be able to at least give some sort of a signal or some sort of a information, whether you are transmitting or receiving. Okay, so that is with respect to the array antennas. And as I was telling you, majorly we should think about patch antennas only, because these are the things which are mostly used and mostly used in practical situations also. So this is the structure of your patch antennas, and these are the what do you call, this is the radiation pattern. Okay, so this is the radiation pattern which is projected here, which is coming exactly again perpendicular to your patch. So if you talk about microstrip patch antenna, it generates an omnidirectional radiation pattern. Omnidirectional means just at the beginning we have discussed what is an omnidirectional, where the radiation is confined to a plane. Okay, so here also if you see the radiation pattern of a patch antenna, it is distributed above the patch. So that means all the plane which is above the patch is being covered. Okay, and underneath your patch there is nothing coming out. Okay, so there is no radiation in the other direction, whereas in the plane which is above the patch, that entire plane is getting covered using your microstrip patch antennas. Okay, and coming to your patch antennas also, when you talk about the fields, how the fields establish themselves. So this is basically due to a phenomena called as fringing effect. Okay, so there are certain conditions which we generally talk in terms of radiation. When do we get radiation? So we get radiation in two cases. One is when you have an acceleration or deceleration of charges. The other one is when you have a sudden discontinuity. Okay, so when you have a sudden or an abrupt discontinuity in your already existing thing, so then you generally start getting radiation. So here also, if you look at the patch or the structure of your microstrip patch antenna, you see that the patch is confined to a particular plane. It's not covering the entire substrate surface. Okay, so there is an abrupt change from your patch to your substrate. So there is a discontinuity which is there at the edges of the patch. So this discontinuity is basically helping or what you call giving rise to this phenomena called as fringing effect, where there is a bending of electrical lines. Okay, so if you look at this picture, there is a patch here, there is a ground here. So both are given in the same color. So both are conductors which are used here, and there are lines of force which will be extending from the patch to the ground. So the lines of force are basically extending from the patch to the ground through the substrate. Now once you come to this point where your patch is ending almost, where your patch material has been terminated, so what happens is, in spite of being terminated, there will be lines of force which would like to extend from the patch to the ground. So that is where this bending of lines is happening. Okay, so at the edges you see So there is a bending of lines which happens. Now when this bending is happening, so there is a possibility of having a discontinuity at this point, because of which the radiation can start emerging out at this point. So basically, because of the presence of this patch over here, the radiation mechanism has started and it will extend into the free space. Okay, so this is what is called quasi-TEM mode, which we call it as transverse electromagnetic wave, or quasi-TEM wave. Okay, in case of waveguides, or in case of microstrip line, or in case of a transmission line. Whereas here you call it as the radiation pattern, which is omnidirectional radiation pattern. And then coming to your wave propagation. So yeah, when you talk about wave propagation, so as I was telling you in the field zones also, so there is a concept which is called as minimum distance criteria, which you have to maintain between your primary antenna or your transmitting and receiving antennas. So whenever you put your transmitting antennas and receiving antennas at a distance of which is greater than 2d square by lambda, so there is a tendency for your wave to travel in different directions. So it can travel straight direction, or it can reach your receiver, or it can travel in either way. It can go and reflect from some other thing and come back to your receiver, and similarly it can reflect from the ground and reach your receiver. So there are so many ways in which a wave can reach your receiver. Now depending on the phase difference that exists at the receiver, whether they are coming in phase or they are coming out of phase, okay, so the signals will add up. So if the signals are in phase, they will add up, and the strength of the signal is increased, whereas if they're coming out of phase, they'll cancel out each other and you don't get any signal also. Okay, so sometimes you might have observed, so what happens generally in high-rise buildings or towers, wherever you have, or even in your mobile cases also, you might have observed where you will see that there is no signal at all. Okay, so why is that happening? So why you don't get a signal at certain point, and why do you get a signal at some other point? So what is the reason for that? Though there is a tower at a common point, why you're not getting signal at one corner of the room and you're getting a signal at some other place in your own house itself? Okay, so the reason is this. So you are getting reflections from various points, and finally when it is reaching the receiver, so the receiver just looks into whether it's a signal which is coming in phase, whether I should add up the signal, whether I should subtract the signal. That's the only thing it knows. So if you are coming in phase, if all the signals are coming in phase, they're adding up and they're giving you the signal. If they're not coming in phase, or if they're not reaching your receiver, so then it's nothing but you are getting a zero signal over there. Okay, so it's basically kind of a reflection which happens because of the presence of various things. Okay, so those all things have to be taken into consideration whenever you are talking about wave propagation, especially from one antenna, from your transmitter antenna to your receiver antenna. There are a lot of things in between which has to be considered whenever you talk about transmission and reception. Okay, so when you talk about transmission and reception, so basically what you are trying to do, you are sending some signal and you are trying to receive some signal, right? So when you are sending some signal, so what you aim for? You aim for that this is the source signal I have sent. Suppose I send 1 kilowatt of signal. Okay, so at the receiver you should be able to receive. Will you be able to receive 1 kilowatt? No, definitely not. You won't be able to receive the 1 kilowatt. But how much amount of signal you will get? So if you see in the practical scenario, you tend to get a power close to 1 milliwatt. So which means how much amount of loss you are incurring, basically because of the environment, or because of the conditions whatever are existing between your transmitter and receiver. So that is what we call it as a transmission loss. Okay, so the transmission loss is very huge. So you are almost receiving how much? You are receiving 1 kilowatt. 1 kilowatt is how much? 10 to the power of 3, right? So 10 to the power of 3, and you are getting 10 power minus 6. That means 10 to the power of 6 is the amount of loss which you are incurring between your transmitter and receiver, right? So you have to look into this particular aspect whenever you are discussing about antenna, especially in receiver antennas. Whenever you are designing your receiver antennas, you have to take care that the sensitivity levels for what you are designing this particular antenna, you are catering to that particular power requirement or not. Okay, so you should not design an antenna at the receiver point which will receive only 1 watt or 1 kilowatt or whatever. You should also take into account that it can happen, there can be a lot of transmission loss involved, and your antenna should be in a position to take care that whatever signal it is receiving, you should be able to take that signal and analyze that signal and get the information from it. So that is the role of antennas, especially in the receiver end. So transmitter end, it's not a big deal, because whatever there is a source connected and whatever is being sent, your antenna is transmitting. Okay, so the main criticality, especially in RF transceivers, okay, or RF transmitter and receivers, are the designing the receiver end. So receiver end is major, what you call major role. It will plays a major role basically, because the sensitivity levels have to be there, and also your whatever you are receiving, based on that you should be able to extract the information, analyze the information. You probably need to change it from analog to digital conversion, and then you need to do some DSP on that, that is digital signal processing on that. Then you have to do a lot of the other things, right? So all these things, if you have to do it, first of all you should receive the signal. So, and this received signal should be tapped correctly, and it should be able to analyze or give out some information. Okay, so all these things are critical. So when you talk in terms of wave propagation, there is a standard equation which we call it as Friis transmission equation, which gives you the relation between your power transmitted, power received, your effective aperture of transmitter antenna, effective aperture of your receiver antenna, and the distance that exists between your transmitter and receiver, and also the wavelength at which you are operating. So this is what is the Friis transmission equation. So where PR by PT equal to AER AET by R square lambda square. So where PR is nothing but your received power, PT is your transmitted power, whereas AET is nothing but effective aperture of your transmitting antenna, AER is the effective aperture of your receiving antenna, and R is nothing but the distance between the antennas, and lambda is nothing but the wavelength at which you are operating. Okay, so this is what is your Friis transmission equation or Friis transmission formula, which gives you the basic relations that exist between your various parameters. So if you take this particular equation into consideration, so what is your power received? So it is basically dependent on your how much amount of power you have transmitted, and similarly what is the effective aperture of your transmitting antenna, what is the effective aperture of your receiving antenna. Okay, so what do you mean by effective aperture? Effective aperture means basically it's talking about that area or that portion of your antenna which is able to what you call involve in the radiation process. Okay, so that means how, though you are having antenna of a huge size or a small size or less size or whatever antenna you are taking, so in that there is only not the entire physical area is going to be involved in the radiation process. There will be only certain portion of the area which will be involved in the radiation process. So that particular area which is actively involved in the radiation process is being termed as effective aperture. So in the case of antenna, transmitting antenna, you call it as AET, or in the case of receiving antenna, you are calling it as AER. So in either it be transmitter or receiver, basically the amount of power that you are receiving is basically dependent on the effective apertures of your transmitting as well as your receiving antenna. So that this is very important thing which you have to observe. So any receiving power, whatever you are receiving, so it can be dependent on these things. And similarly the distance, so how much amount of distance you are maintaining between your transmitter and your receiver, that also is going to decide how much amount of power you are receiving. So if you are placing your transmitter and receiver quite far off, so then definitely the amount of power received will be less. So there is an indirect relation existing between your received power and your distance of separation between your transmitter and receiver. And similarly it comes to the wavelength also. So PR is basically inversely proportional to lambda square, which means that the lesser the wavelength, the more the power. Okay, so the lesser the wavelength, the more the received power. So that's what, again it comes back to the same thing. So you are operating at high frequencies, wavelength is going to be less. So when you are having wavelength less, definitely the amount of power that you receive is also going to be more. So that's the reason why we go or prefer for the higher frequencies. Okay, so thank you on that. So if you have any specific doubts, just let me know so that I can answer your queries. Any specific doubts?
Ma'am, can you show us ninth slide one more time?
Yes, yes.
Can you show us the ninth slide?
Ninth slide. Okay. So what is the ninth slide?
The microstrip antenna.
Yeah, yeah. Tell me.
Yeah, I couldn't hear the part, ma'am. That's it. Like why waves go down.
Okay, so basically why I'm specifically stressing on microstrip patch antenna is most of the mobile applications are basically using this micro patch antennas only. Okay, so the basic structure is known to you. So you have a ground, and followed by that you have a dielectric substrate, on the top of which you have a patch. Okay, so these patch can be of any shape. It can be a square shape or a rectangle shape or a circular shape. You can take any shape. Okay, basically when you talk about patch antenna, it's a antenna which generates a radiation pattern which is omnidirectional. Omnidirectional in the sense it's confined to a particular plane. It is spreading out in different directions, but it is confined to a particular plane. Like you see here in this radiation pattern, it's above the patch. Okay, there is nothing radiation emerging out of below the patch. So nothing is coming out at the edges also. It's only confined to a particular plane. Okay, so it's only confined to a plane. And I told you in this context, what I've told you is that the length, width and thickness of the patch are going to basically determine the kind of radiation that is being emitted out from the patch antenna. So here you have length, thickness and height also. Okay, so that determines how much amount of thickness you have taken or how much amount of length or width you have taken. That is going to decide what will be your radiation pattern. And when you talk in terms of radiation pattern here, so I told you that there will be fringing fields. Fringing means actually bending. Okay, there will be bending fields at the edges of the patch, which are basically giving rise to radiation. Because you know that the conditions required for radiation are talking about having either you have an acceleration or deceleration of charge, okay, or there is an abrupt discontinuity which you have in the already existing uniform current. So here basically that is what is happening at the edges of the patch. So you have a substrate on the top of which you have a patch. So here at the edges of the patch basically you have a discontinuity because there is a change in the medium in which the waves have to travel or the fields have to travel. So when you talk about this microstrip patch antenna, so here patch is basically a conducting material, ground is a conducting material. So when these two are conducting materials, there are electric lines of force which extend from patch to the ground, which are actually traveling through the substrate or through the dielectric. Okay, whereas when you come at the edges at this point, so what happens now, the patch has ended abruptly, so it is not extending throughout the substrate. So now what happens, the electric lines of force whatever were extending from patch to ground, when they see an abrupt discontinuity, they won't stop there, they'll just try to bend and try to reach to the ground because they see that there is no medium over here. They still exist which will be extending beyond the patch. Now when this happens, there is basically a kind of a discontinuous nature which is existing at the edges of the patch, because of which the radiation mechanism starts or emerges at this point. So the fringing fields are the main reason for which your radiation starts. So once the radiation is established, and then you get a what you call a radiation pattern similar to this kind of thing. Is it clear?
Yes, ma'am.
Yeah. So anything else which you would like to know? Just shoot out, because I have just prepared in brief whatever will be required from this perspective, whatever your placement people have given me. So if you require any other things to be clarified, I'll just shoot it out. I'll try to clarify.